Today what I would like to do is pick up with the RSP spectrum analyzer. If you watched the earlier video on this, the introduction to the RSP spectrum analyzer, you're already familiar with the fact that this is a spectrum analyzer software set or piece of software that runs on the RSP series of software-defined radios. I went over briefly what this is all about in the introduction, so I won't go much more into that today. But what I would like to do is spend some time actually looking at the spectrum analyzer and its characteristics to see how capable it is and how it might be used in someone's amateur radio activities or hobby, or perhaps even some commercial activities. Now understand, this is not intended to be a laboratory quality spectrum analyzer. Those cost thousands of dollars. They used to cost hundreds of thousands of dollars. Today, it's really a miracle that due to the ability to digitize at very high rates, that we can have equipment like this that frankly 20 years ago was out of the reach of even fairly well-off amateurs and hobbyists and so on. So what you see on the screen is a sweep that covers the full range of the RSP spectrum analyzer. It starts at 1 kilohertz on the left, and I'll show you this in a minute, and goes to 2000 megahertz, in other words to 2 gigahertz on the right. And all it is displaying is what it detects through a Wi-Fi antenna. In other words, there is an antenna that, if you watched some of my videos on the Mini VNA Tiny Plus, you have already seen this antenna. It has a resonance around 2.4 or so gigahertz. So the actual antenna resonance would be out here to the right, above the frequency range of this particular unit. But nonetheless, it does give you an idea of the sensitivity of this device. Now what you're seeing is basically all of the RF that is flowing around in my little home lab shop, whatever you want to call it. There's a router, a Wi-Fi router that produces a lot of signals. Obviously most of that is up here as well. But I also have a lot of equipment which have switching power supplies and all sorts of things that generate, and then there is all the broadcast interference, things like FM, which would be probably down in around this area. And then notice that there are some fairly tall spikes down in the FM region. And then there is a relatively tall spike at about, I am going to guess that's about 370 or 380 megahertz. And another one here just below 600. So I'm going to show you in a minute another spectrum analyzer with an antenna sweeping the same range. And notice that there's a peak a little below 400 and a little below 600. And then there's a bit of higher spikes out in this end. So let's switch now and take a look at another spectrum analyzer doing pretty much the same frequency sweep. Here is the display covering the same 2 gigahertz of bandwidth. On the InStick, this is a GSP 730 that I'm sure if you've watched my videos you've seen before. Once again, you notice that There are some signals down here in the FM band, and then there are some peaks up here, as we saw in the other display. In other words, the general shape of this is about the same, and then notice up here at the end, around 2 gigahertz, it starts to rise a little more. Now, part of this is the activity around the Wi-Fi band, which once again is just a little above the range I'm sweeping here. This particular generator will, spectrum analyzer will go to 3 gigahertz, but I'm restricting it to 2 so that it is comparable to what you saw on the RSP spectrum analyzer. Now, let's move over and take a look at the Rigol displaying pretty much the same. I say pretty much the same because the Rigol, the DSA 815, only goes to 1.5 gigahertz. So on the right here is 1.5 gigahertz. But nonetheless, you notice that there are some, once again, peaks down in this area, and then kind of a fall off, and then some even higher peaks in this region, and then a fall off and fairly quiet for a while. So what I'm going to be doing is taking some measurements with the RSP and then comparing them to one or both of these spectrum analyzers. Now, I have a third spectrum analyzer which is made by Siglent that you see over here. I'm not going to be using it, partly because this is a little expensive, $2,600 I think, or so, $2,700 is a little expensive for the average hobbyist, amateur radio operator, and so on. This unit is getting a little long in the tooth. It's been around for a while. It originally cost less than $1,000. The Rigol, depending on where you buy it and what you have equipped with and whether you buy new or used, can be had for around $1,000 on the used market. A little bit more than that if you buy a used one, especially with the tracking generator, which if you're going to buy one of these, I would suggest you use the tracking generator. But my purpose here is not to try to sell you on any of this equipment, simply to show you how the RSP spectrum analyzer works in comparison to these two. Now, the swept frequency spectrum analyzer actually switches a series of bandpass filters, or a single bandpass filter, across a range of frequencies. Most of the equipment that you buy today uses a form of fast Fourier transform. Now, in some cases, they do use a resolution bandwidth filter, but they still process the signals using an analog to digital converter and software. So the day of the purely hardware spectrum analyzers that existed back in the 70s and 80s has pretty much been supplanted by these half hardware, half software. And that's kind of what the RSP spectrum analyzer is. It uses the software-defined radio for the hardware, and then it does most of the signal processing in the computer that it's connected to with the USB cable. So let's take a look at the setups. Over here you see what I have is just a simple antenna with the length extended about the same height as the other ones. Here is an antenna, and I just have it stuck out this way. I understand this is more horizontal polarized, whereas this one is vertically polarized. And then the one that I was using on the RSP is down here. And once again, those of you that remember the Mini VNA Tiny Plus videos, we characterized this antenna using the mini VNA and a couple of other instruments to look at its reflection and SWR and so on over a band of frequencies. So the first thing that I'm going to be doing is applying a single signal to the RSP spectrum analyzer in order to determine what are the limits of its measurement ability. In other words, how small a signal will it take, how large a signal will it take, or for those of you more in the know, what is its dynamic range? Where's its noise floor and what's the dynamic range? I am generally going to be using this HP frequency synthesized signal generator as the source of signals. And the reason is, first, this is a very trusted piece of equipment. You see it in a lot of labs. It's also been around a long time. I also have a lot of confidence in this particular one. I've had it for quite some time, and the calibration, I had it calibrated when I bought it. I bought it used, and I then stored the calibration with a series of other devices so that I could check it from time to time. And so I am fairly confident that this unit is quite well calibrated, and it has a very good reputation for things like phase noise and other things that some generators frankly aren't as good at. So that's what I'm going to be using. What I have on the screen right now is a 1 megahertz signal at a level of -30 dBm. Now, for those of you that are not familiar, dBm just means dBs relative to a milliwatt. The M stands for milliwatt. So this means 30 dB below a milliwatt. Okay, that's what we have there. Now let's look on the RSP software and see what we can display. This is the display on the RSP, and the only thing that I have between the generator and the RSP is a DC block. I'll talk about that a little bit later. That's just a safety feature that I like to encourage people to use. It helps keep you from damaging your spectrum analyzer, or in this case the SDR receiver that's the basis of the spectrum analyzer. So what do we have on the screen? Well, this is a 1 megahertz, and notice it reads right at 1 megahertz. And I have reduced the effective resolution bandwidth, and we'll talk about that in a second, so that I could display these two sidebands. Now, what those sidebands indicate is that there is some amplitude modulation present. Now, I suspect that it may be that, I know this is not from the generator, so I suspect that the front end of the RSP 1A that I'm using may be generating these. But notice that our signal should be -30, and it shows very, very close to that. In fact, the difference here very well may be just the cable, the loss in the cable and in the DC block. So I'm going to say that as far as the measurement capability of level, it looks very, very close, very accurate. Certainly well accurate enough for most applications outside a measurement lab or a very exacting commercial environment. These sidebands do give me a little bit of concern, and what I'm going to do is I'm going to go over here, and I hope you can see what I'm doing. The number of FFT bins, or another way to measure it is over here to the right, it says the number of hertz per bin. I have right now set to 61.5 0.04, 61 hertz per bin. I'll talk about that in a little bit, what we really mean there. But let's look at what happens to the signal when I change this NFFT. Now, it started out at 4096, and notice how blocky everything looks. Now we go, and by the way, that's 488 hertz per bin. So I'll explain this in a little bit for those of you that don't realize what's going on here. There's nothing unusual about this. It's just the way that FFT software works. Here is 8192. Here is 16. And as I got to 16, let me go back to 81. And here you notice you don't see those sidebands. When you go to 16, which is about 122 hertz per bin, you start to see these little sidebands. Then, when you go to 32, you see them even more pronounced. So let's also go to 65, which is going to put about 30 hertz per bin. There you not only see those, but you also see a couple of others starting to creep up here. By the way, notice that the resolution of this display is starting to get finer and finer. The span isn't changing. In other words, what frequency is on the left and what frequency is on the right, what frequency is in the middle, those aren't changing. What is changing is the actual resolution. In other words, how finely it is looking at the signal. Now let's go to even more bins. Okay, now notice a couple of things. One, the display is starting to slow down. It's now updating about once a second. At the next lower figure, notice how fast the display jumps. That's an update. So it's updating pretty fast at 30 hertz per bin. If we go to 131, by the way, you may notice these are powers of 2, or 15 hertz per bin. Notice how it slows down. Well, let's go even further. Let's go to its maximum ability. There, you see, we are able to discern some very fine detail in this FFT. Now, what I'm going to do is I'm using a 5 kilohertz span. I'm going to now go down to a 2 kilohertz span, and I hope you can see this up here where I'm doing this. Click on 2 kilohertz. Now you see what we've done. Now we have changed the span. We've spread it out a little bit. So here is the carrier, if you will, or the frequency out of the generator. And then at around 2 kilohertz, just under 2 kilohertz, there is an upper sideband, and just about 2 kilohertz below, 9980, there is another. And then notice that there is another harmonic here, one here. See how these flows down like that. And similarly on this end. Now, they are coming and going. Well, I said they are. Yeah, as I move my arm, watch the left-hand side as I move my arm in here. I get a different reading. If I sit still, I get a fairly stable reading. What that is telling me is that there is some kind of external signal that is mixing with this 1 megahertz. I suspect it's a local broadcast station. That is an AM broadcast station. Remember that the AM broadcast band is 550 kilohertz to about 1.6 megahertz. So, in other words, we're right in the middle of the broadcast band here. And I think what we're getting is intermodulation with a local broadcast, AM broadcast station. Well, let's not speculate. There's something else going into the signal. So what I want to do now is try this same signal on another spectrum analyzer and see if I see the same thing. So I'll be back in a little bit after I've done that test. Here is the same signal displayed on the Rigol DSA-815 with 100 kilohertz of resolution bandwidth. And remember, on this one we were using 3 hertz per bin at the low level, at the finest resolution. So the this particular spectrum analyzer will only go down to 100 hertz resolution bandwidth. I have the reference level set the same, minus 20 dBm. Notice we're not seeing those same sidebands. Now, occasionally you do see some level, but this is a 5 kilohertz span, so a 2 kilohertz signal would show up around this area, and you notice that there's noise, but there's no sidebands. So I suspect that the RSP1 is picking up some local broadcast, and because it only has a plastic case, it's probably not shielding nearly as well as, for example, the Rigol. The Rigol's front end is very well shielded. So we've discovered of the first issue is there is a small amount of intermod down in the broadcast band, at least with my RSP1A, or at least I think that's what's going on. So now let's take a look at something a little higher up in frequency, maybe around 10 megahertz. It occurred to me that that it might be a good idea to use another USB spectrum analyzer. This is the Signal Hound SA44B running the Spike software, and we have pretty much the same thing. At the top is we have a resolution bandwidth of 10 hertz. The center frequency is a megahertz. Just a little there. You can see it at the bottom, right here. The span is 2 kilohertz, and you notice that we do have around minus 80 dB. We have those same two spikes. So the upper and lower sideband. So I may have to revise my my guess that this is occurring in the front end of the RSP1A, because the Signal Hound, I know, is pretty well shielded. It has a metal case, and I have not noticed this kind of thing. So it's very possible that what we are seeing is a result of intermod that is getting into the system, perhaps even through the power line, and is causing these little sidebands. Now understand, this is very low level. We're referencing to minus 20 dB is the reference level. Notice that's right up here. So this is minus 30, which is what we're outputting from the generator. Now, it's not uncommon when you are referencing, you're using low-level signals, and I'm deliberately keeping these low-level at this point to avoid overloading anything. But when that happens, signals that you otherwise might never have noticed, and frankly I've never seen these before, but they very well may be coming in through the HP generator because we're using such a low-level output that little things that normally wouldn't matter are showing up. So I want to revise what I said earlier and say, okay, this is not necessarily a problem with the RSP1A. This very well may be spurious signals that are coming through just through my lab in one way or another. I've reduced the output of the HP generator to minus 130 dBm. And I've reset the reference level of the spectrum analyzer to minus 100. So, in other words, the top of the screen, or the camera there, the top of the screen is a minus 100 dBm, minus 110, minus 120. This is minus 130. Notice that the noise is beginning to intrude around minus 140 dBm. So this is only 10 dBm above the noise floor, and this is very impressive. It's a very, very low noise floor, and what it tells me is that the RSP1 has a very sensitive front end that does not introduce a lot of noise into the signal. Being able to see a minus 130 dBm signal is quite good for a low-priced spectrum analyzer like this. So I'm quite impressed at a megahertz. We need to, of course, go up and try a few things at 10 megahertz and maybe 100 and a gigahertz and maybe up near 2 gigahertz. But for right now, this RSP1 with the RSP spectrum analyzer software is doing a very good job. And this is that same minus 130 dBm signal at 10 megahertz. Notice it's picking it out of the noise quite well, displaying it very accurately. So let's try 100 megahertz. At 100 megahertz, it's doing even better. Notice how much lower the noise floor is at 100 megahertz. And we're still accurately reading the minus 130. So let's try a gigahertz. At a gigahertz, the calibration of the RSP is starting to show a little bit. Notice that instead of the peak being right in the center at exactly a gigahertz, it's at 100, a little above 10007 gigahertz. Okay, at 2 gigahertz, or actually I have it at 1999, here is the signal. You can barely see it. The reason is the noise floor. The noise floor has come up to, minus 140 plus and minus. What I'm going to do is raise the signal level to 120, minus 120, so you'll be able to see it a little better. That's 120 exactly. So there you see it's starting to come up out of the noise. This, once again, is still very impressive to be able to go all the way to 2 gigahertz and still be able to display a 100 and minus 130 dBm signal is quite impressive. Okay, here is a signal at 1.999 gigahertz. I'll explain in a second why that you have to go a little bit below 2. And in the center is the signal at a minus 120 dBm. Notice that there is a spurious signal. I'm going to turn off the RF from the generator. There, it's off. But you notice this spurious signal is still there. Turn the generator back on. By the way, there's one here too. Back on. And now the question is, why can't you go to 2 gigahertz? Well, it's because it turns out that the ending frequency can't be higher than 2 gigahertz. There you see it with a narrower effective bandwidth or resolution bandwidth. And as you see, it really pulls the signal out of the noise. Now let's go to a 2 kilohertz. I'm at a point where the resolution of my generator causes the frequency to move quite a bit. We're at such a very narrow resolution here that we really are looking at that. But look at what has happened to the noise floor. It's now down around minus 150 dBm, and this minus 120 signal is coming out quite easily. I want to go back down to minus 130. There is a minus 130, and notice you can pick that out without any trouble at all. Now, there's a lot of noise, of course, at these, because we're really down in the noise level here. But with the high resolution bandwidth that this is capable of, let's go to its best resolution bandwidth. There you see it drives the noise down. Almost all the noise is below, is lower than minus 150 dBm. Once again, at 2 gigahertz, this is really impressive. So I'm going to be doing a few more experiments, and I'll put those probably in another video. For right now, I want to go ahead and get this one posted because I've basically run over the frequency span of the RSP 1A, which is up to 2 gigahertz. We have driven it to its absolute noise floor and found that its performance is quite incredible for an instrument of this cost. So I want to wrap this up. I will do a part 2, but for right now, I just want to say in summary, the RSP-1A with the RSP spectrum analyzer software, I think is a wonderful piece of equipment to add to your lab. It is such low cost that a lot of people will be able to afford it who can't afford the expensive $1,000, $2,000, $5,000, $200,000 spectrum analyzers that are out there. So I hope this will encourage you to, if you have an RSP1, to go ahead, or an RSP2. I know it will work with the RSP2 as well. I haven't done as many experiments with the 2 because I mainly wanted to use the cheaper one. But it seems to work very well, and I'm sure it would perform equally well with the RSP2. So for now, hope you enjoyed the video, got a little out of it, and it encourages you to go do some of your own experiments. Look forward to a part 2, and in the meantime, have a nice day.